Hello and welcome to what for now will be the last of these short chats about dasim. This time looking at frequency and step responses. Again, two topics that we won't be talking about in lectures until the spring term, so if you're watching this in the autumn term, maybe just watch this for interest or put it on file and watch it again in the spring term. Now, frequency and step responses correspond to circuits which have outputs which are a function of frequency. Let's look at a simple example. This one here. We have a voltage source, 1 volt in this particular case, going through a resistor and a capacitor, and the output is being measured there. It's currently set up to do a DC simulation, which is why the output is measuring 0 volts. If I flick across here and go to AC analysis, we can see that the output across this capacitor is actually 846 millivolts with a 1 volt alternating source coming in there. So the voltage there is oscillating between plus 1 volt and minus 1 volt, going up and down like this. And the voltage across my capacitor is going from plus 846.7 millivolts to minus 846.7 volts, up and down as well. But the amplitude across the capacitor is a function of the frequency. If I change the frequency, it changes. It goes up at lower frequencies, and at higher frequencies, it goes down. Frequency responses are a way of plotting the amplitude across the capacitor in this case, although in general, the amplitude measured by the voltmeter, wherever it is, as a function of frequency. It's a very common and useful thing to want to do, especially when designing filters. The simulator will do this for you. You just click on the frequency response simulation and a little graph of amplitude in dBV against log of frequency. This is a logarithmic scale, note, 1 Hertz, 10 Hertz, 100 Hertz, 1 kilohertz, and so on, appears on the screen here. If I want to get rid of the phasor diagram here, I just click AC analysis again, and I'm left just with the frequency domain plot here. You can select what range of frequencies are being displayed by choosing one of these 4 options. Low frequencies, up to 10 kilohertz. Audio frequencies, roughly from 1 to 20 kilohertz, but it plots it up to 100 kilohertz. High frequencies, which is 100 hertz up to 10 megahertz, or RF going all the way up to 1 gigahertz. For these particular component values, it's probably the high frequency one which is most appropriate. And you can see that the frequency response, that's a measure of the amplitude of the output in dBV against the frequency, has the shape of a line like this, a horizontal line at low frequencies, and a sloping line at high frequencies with a sort of curve in between. If you've come across the Bode approximation, you can also plot the Bode approximation like so. And that would be those 2 low frequency line and high frequency lines just extended until they meet at that point there, known as the break or corner frequency. The phase, this 81 degrees here, that's also a function of frequency. See, it goes down to pretty much 0 degrees at low frequencies and up to around about minus 90 degrees at very high frequencies. And you can also plot the phase of the output as a function of the input by clicking the Show Phase button. You get a scale here from plus 180 to minus 180, and the phase is displayed as this dotted line here. Memory. Memory allows you to remember a particular shape of this curve, put it into memory. I can then change the values of one of these components, maybe take this up to 10K, And the memory one, the one that I remembered, is still shown in light blue. So this darker blue is the current display. The lighter blue one is the one I memorized when this resistor was 1K. So I can compare. I can see the changes that have happened in the frequency response plot by changing the value of that resistor. Get rid of the memory, just unclick that checkbox. Right, it's showing dBV at the moment because that's a voltmeter. If I'd put an ammeter in the circuit, I would have the option of making the y-axis units dBA and plotting the current against the frequency. But that's a much less common thing to do. Okay, I think that's all you need to know about frequency responses to get started. Now, step responses. The step response is the output of a circuit when its input is a step. And an input step looks like this. This goes up to 1 here. This is time t equals 0. This is the voltage. That is known as a unit step. Voltage is 0 for all negative times and 1 for all positive times. And if that input goes into a circuit, the circuit will have what's known as a step response, and the step response is a graph of the output of the circuit against time. In this particular case, we would expect it to look like this as the capacitor charges up to 1 volts. And we can see that in the step response here. This slider here changes the time scale. So just looking at the very first bit of the step response, it looks like a straight line, but that straight line soon curves off, and as you get towards the end of the step response, it's a horizontal line at about 1 volt when the capacitor is fully charged. And we've seen this shape before on the transient simulator. This is a much faster way to get to the step response rather than having to do a full transient simulation. Once again, we have a memory button so that we could change this 10K to a 1K and see what effect the value of that resistor has. The light blue curve here was the value of the step response when the resistor was 10K. The dark blue is its current value with a 1K resistor, and you can see that the shape of the curves is similar, it's just that one is happening much faster than the other one. Fixed axes is a bit like the autoscale function in the XY simulator. It means that any changes that I make, the axes here from 0 to 1 volt don't change. Otherwise, it will try to autoscale the y-axis values to fit all of the transient step response onto the screen. You can show both the frequency response and the step response at the same time. Just enable both of them. And I think that's about it. It can be quite instructive sometimes to, for example, let's put in a variable resistor here and allow it to change between 1K and 10K. And I can now see how both the frequency response and the step response change as the value of that resistor changes. Okay, that brings us to the end for now of the little videos introducing the simulator dasim. Some of them won't make a lot of sense at the moment, but do remember they are there because they will be a useful resource to come back to when we start studying frequency response and step response in a lot more detail later on in the module. In the meantime, enjoy and do let me know if it does anything odd.